Alright, welcome back to CSE 222, and today's video is being brought to you by one squirrel and two gargoyles. And the subject of today's video is graphs and graph theory, but more looking at the mechanics of graphs and how we can interact with graphs in a computer program. So, what is a graph? I'll give you the most hand-wavy definition of a graph. It's a bunch of dots and a bunch of lines connecting some of these dots together. So there's an example of a graph, right? And these dots are called vertices, or sometimes nodes. And the lines connecting these dots are called edges. Now, CSE 215, our discrete structures course, we spend a few classes talking about graph theory, and we get into the sort of more formal definition of this. But when you think of a graph, just think of a series of dots and some lines connecting them. And so, you know, we could have more dots and more connections. And the main thing to remember about graphs is that the way we draw a graph on a piece of paper is not significant. What's significant is the set of vertices and the set of edges connecting those vertices. So for example, if I draw a graph like this, 4 vertices, 4 edges, or I draw a graph like this, 4 vertices, 4 edges, these are exactly the same graph. And we can see that they're the same because if I label these A, B, C, D, and I label these A, B, C, D, that helps you see that these are exactly the same, right? I switched the location of C and D on the paper, but if I switch them back, right, my line from A would come straight down to D just like that, and from D we'd go over to C, and C would go straight up to B and A. So it would look exactly the same. And you can think of this as, you know, push pins that you put into a corkboard connected by rubber bands. And as long as you don't break any of the rubber bands, you can pull these pins out, move them around, put them back into the board, and you end up with the same graph. So the way we're going to work with graphs inside a computer is going to be independent of how we might actually draw this graph on paper. And the only thing we're going to need to worry about is what are the set of vertices and what are the edges connecting them. So we can keep these images in mind, and when we work on graph problems, we'll draw pictures like this. But don't get too concerned with how we chose to draw this particular picture. I drew this edge to be curved, but I could have drawn it, you know, as a pair of sharp lines like that, or I could have drawn it as, you know, a wavy line that does all kinds of crazy things and eventually comes back here. It would be exactly the same graph. And when we have a graph, we can associate weights or numbers with these edges. So I might give this a weight of 2 and 4 and 1 and 3 and 6 and 5 and 2 and 7 and so on. And we could think of these weights as having particular meaning. For example, if this was a graph that corresponded to cities and these edges corresponded to roads connecting one city to another, then these weights might be the distance that you would travel from one city to another. Or if these were cities and these were airline flights, these could represent the number of hours that it takes to travel from one city to another. Or it could be the cost if these are toll roads that you would have to pay to get from one city to another along this road. So we can have weighted graphs, or we can have unweighted graphs where we just have edges with no particular weights associated with them. And we can also have directed graphs. We can have a graph where we think of this edge as going in a particular direction. And each of these edges might have a direction associated with it. And it's possible that, you know, there could be an edge going back in this other direction. And that could have a different weight from the edge going in the first direction. And there's going to be nodes that perhaps do not have any edge connecting them. or edges that only travel in one direction, and so on. We can have graphs with negative weights, and those end up being very different from graphs that only have positive weights. So there's a lot of different varieties. We want to look more, like I said, at the mechanics of how we work with graphs, how we represent them in memory, and I also want to talk about one algorithm in particular that we use when we work with graphs, an algorithm for finding the shortest path between 2 points. That's something called Dijkstra's algorithm, and that may also be a programming assignment that you get at the end of this course. So let's think about how we can represent graphs in memory, because we can represent them on paper by just drawing dots and lines, but we can't do that inside the memory of a computer. So let me make a neater looking graph here. So let's suppose we have a graph like this. So I will call these vertices A, B, C, D, E. So one easy way to represent a graph is with an adjacency matrix. And the idea of an adjacency matrix is we make an entry in our matrix for each vertex. So if we have 5 vertices, let me make a 5 by 5 matrix. Like this. And what I'm going to do is record whether there is an edge connecting any pair of vertices. So for example, A is connected to B, C, and D. So I would put a 1 here, here, and here. There's no edge connecting A to E. There's no edge connecting A to itself. B is connected to A and C and D. C is connected to A, B, D, and E. D is connected to A, B, C, and E. And E is connected to just D and C. And so there's a 5 by 5 matrix. This is a binary matrix or a Boolean matrix, and it shows the connectivity between vertices. So for example, is there an edge connecting A and E? Well, I can look at A and go over to E. I see a 0 there. Nope, there's no edge connecting those. What about A and B? Yes, there is an edge connecting A and B. So if we store this in memory as a 2-dimensional array, for example, we have all the information we need about the graph. Again, there's nothing saying that, we drew A to the left of B and below D, but that information is not relevant. That's just how I chose to draw this particular graph on paper, but that's not part of the graph itself. And so we can tell a lot of things from this matrix. First of all, obviously we can tell how many vertices there are. It's a 5 by 5 matrix. There's 5 vertices. We could also tell how many edges there are. Now, how would we know that? Well, we could count up the number of ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Total of 16. Well, if we take 16, so the number of ones equals 16. 16 divided by 2 is 8. We should have 8 edges in this graph. 1, 2, 3, 4, 5, 6, 7, 8. And that's simply because, if there's an edge from A to C, it will show up in row A, column C. It'll also show up in row C, column A. So the edges get counted twice. We can also calculate what's called the degree. The degree of a vertex is the number of edges connected to it. So the degree of B is equal to 3. The degree of E, there's 2 edges connected to E, so that's 2. Well, we can calculate degree really easily. Just add up across each row. If we add up across row B, 1, 2, 3, that's its degree. If we add up across E, 1, 2, that's the degree of E. So we can calculate degrees of vertices also, just by looking at the matrix. And if we had weights associated with these, so let's say this had a weight of 5, and 1, and 2, and 4, and 3, and 2 and 1 and 6, right? Then we could fill this in. Instead of just putting a 1 or a 0, we could say, okay, from A to B, we have a weight of 3. And from A to C, we have a weight of 2. And from A to D, we have a weight of 5. And so on. So we could fill in all of these with the weights corresponding to each edge. All right, now this is for a graph where I did not have any arrows. That's called an undirected graph. And you notice in an undirected graph we have symmetry about this diagonal. Well, we don't anymore because I changed the 1s to 3, 2, and 5. But if there's a 1 in a particular row and column, that 1 will also be in the corresponding column, comma, row. But if we have a directed graph, for example, A, B, C, D, so maybe we have an edge here and an edge here. So something like that. So we could make our adjacency matrix as follows. And we have to choose which dimension we're going to use from and to. So I'm going to put a little line here and say from to. So if I put an entry right here, it means I have an edge from A to B. All right, so A is connected to B, and that's the only edge from A to any other vertex. From B, we have an edge going to C, and we have an edge going to D. C, we have an edge going to A and also to B. And, you know, we could also have edges that go to themselves. And so D might have an edge going to itself and nothing else. And so this would be the adjacency matrix for this directed graph. And again, if we count up the number of 1s, 1, 2, 3, 4, 5, 6, that should be the number of edges in our graph. 1, 2, 3, 4, 5, 6. So for an undirected graph, we have to divide by 2 because we're implicitly counting, you know, each edge twice. But for a directed graph, we just count up the number of 1s. That's the number of edges. So this is one way to represent graphs in memory. Now it's potentially an expensive way if we have a lot of vertices. If we had 1,000 vertices, we would need a 1,000 by 1,000 matrix. If we had 1,000,000 vertices, we need a 1,000,000 by 1,000,000 vertex. Now when would you have a graph with 1,000,000 vertices? Well, maybe if you're a service provider and you're distributing content to 1,000,000 users, you could have a graph showing the path that your content takes from your source server to each of the customers. And that could look like a graph. And it could be, you know, a very large graph. And in that case, it might be a sparse matrix. It might be a matrix that mostly has zeros. You might have a lot of vertices and not too many edges. And so adjacency matrix like this could be wasteful. Now we can do things to deal with sparse matrices, but it might be a lot of memory that we don't really need to spend. So let's look at some other ways to deal with coding information about a matrix. So another option is an adjacency list. And so our setup here, let's make a graph. And I'll just stick with, you know, undirected, unweighted graphs for now. But there's nothing magic about that. So an adjacency list, we would make a list, could be a linked list. We know about linked lists, right? Could be a linked list for each vertex. And we basically just list all the vertices connected to that vertex. So A is connected to B, and it's connected to C, and it's connected to E, and it's connected to F. And B looks like it's connected to A and E, and I think that's it. And C is connected to A and D. And D is connected to, looks like, C, E, and F. And E connects to A, B, and D. And F connects to A and D. And so this also captures all the information that we need about our graph. And so again, if we count up the number of entries in each of our lists, in this case we would get 4, 6, 8, 11, 14, 16 divided by 2, we get 8. 1, 2, 3, 4, 5, 6, 7, 8 edges in our graph. Right, so it's coding the same information as our adjacency matrix, but storing it in the form of a set of linked lists. The advantage here is we only store a piece of information if there's an edge. So if we had a million nodes, we would have a million linked lists, but each one would not be a million elements in length. It would only be as long as the number of edges connecting to that particular vertex. So it's much more space efficient. And we know how to do linked lists. They're pretty easy to work with. They can grow if we had a network that was, changing over time and adding or deleting nodes. We could modify this pretty easily, and it stays space efficient. All right, one other way to code information is called an incidence matrix. And an incidence matrix, we label the edges. So let me use lowercase letters for our edges. So let me call this M, N, P, Q, R, S, T, and V. And so in our incidence matrix, we have one dimension where we store our vertices, and another dimension where we store our edges. I should have made them sequential. There we go. And we simply record which edges are connected to which vertices. So A, for example, is connected to M, P, R, and V. So M, P, R, and V. And zeros elsewhere. B is connected to M and N, and zeros elsewhere, and so on. And again, we could have weights associated with these edges, so we could, put things other than 1 in here. And if we wanted to have a directed graph, we could, only list edges that start from A, for example. And so if we had an edge going from A to B, we would list B. If this edge was going from C to A, we would not list it under here, but we would list it under C. And if we wanted to store weights, we could just make a more complex data structure for the type of data we store in our linked list nodes, and we could store weights and whatever other information we wanted. An incidence matrix, it's harder to store directed information, right? Because we're just saying, is this edge connected to this vertex? But we could also store weights in here and so on. So there's a variety of ways, and we can stick with just a plain old adjacency matrix for the sake of thinking about algorithms and how we could manipulate graph data inside a computer. This is perfectly fine. These other approaches, adjacency lists, incidence matrices, are more related to efficiency of processing. All right. So one thing we can do with graphs is we can look at the question of paths. And so a path is really just a way to start from one vertex and travel to some other vertex. And when we travel along a path, we have to stay traveling along edges. So for example, I could not go directly from A to E. There's no edge connecting that. But I could go from A to D, and from D I could go to E. So there is a path from A to E with a length of 5 plus 1 is 6. I could also travel from A to B, that's a length of 3. B to C is another 4, and C to E, that's 4 plus 3 is 7, 6, that's a path of length 13. I'm using length to say these numbers represent distance, but it could be time, cost, something else, right? So there's generally multiple paths from one vertex to another. And a question we encounter sometimes in computer science is, what's the shortest path from one vertex to another? And, you know, just looking at A to E, there's a lot of possible paths. I could go from A to B, that's 3. Up here is 4. Down here is another 2, is 6. And then up here is 12. Or, you know, I could go 3 over here. 1 up here is 4, and 1 more is 5. And that's a path that involved 1, 2, 3 edges, but was shorter than my path that only had 2 edges, taking a distance of 5 and 1. So why would we want to do this? Well, for example, if you're making a video game, and these could be positions where characters can be situated, and this is distance between those positions, and maybe the player is located at vertex A and there's an enemy at vertex E, and that enemy is trying to get to the player so they can attack. So you would like the computer to be able to figure out what's the shortest path that you can take from E to A, right? Assuming that E's not flying, it can't just, you know, come straight across in a straight line. You have to follow these roads, for example. What's the shortest path that it could take to get to player A? And, you know, coming down here and here might be the fewest number of steps, but it might be faster to come down here and then over to here and then across here. And as player A is moving and as player E is making progress approaching A, the optimal path might change. So we want to be able to compute the shortest path efficiently, and one way to do that is to use an algorithm called Dijkstra's algorithm. So this is what some of your homework questions, your practice problems will deal with, is this shortest path algorithm, and it's called Dijkstra's algorithm. Let me write that more cleanly. Alright, this is an algorithm for finding the shortest path in a graph. It's an undirected graph. It's weighted, right? I mean, the weights could all be 1. We could still treat it as a weighted graph. But the weights cannot be negative. The reason being, if you have a negative weight, that kind of means that, like, each time you go down there, you gain time, and you could just, you know, make repeated loops down that, and you know, end up taking negative time for your trip. So Dijkstra's algorithm works with a weighted graph where the weights are, let's say they're all positive. There could be weights of 0. I don't think that'll break anything, but let's just think about positive weights. And so let's do this by example. Let's start off with a graph. That looks like this, and let's say we're trying to go from point A to point B. And we'll put some weights in here. So let's suppose this is a weight of 1, and this is a weight of 3. And let me throw a few more edges in here. Alright, so we want to find the shortest path from A to B. Now, you know, you and I, we're endowed with this brain that can process images and do some sort of parallel processing. And so we could look at this and we could probably figure out a shortest path pretty easily. But we want to figure out a fixed algorithm that we can teach a computer that it can use to solve this problem. And so we've got this graph stored inside the memory of a computer. Let's just assume it's an adjacency matrix, but the representation isn't really critical. But let's talk about the steps we can use to find this shortest distance. So we have a few notions. We have a notion of a tentative distance. And this is the best solution we found so far. And initially, the best distance to most of these nodes is infinity. We don't even know if we can reach these other vertices, because we haven't explored that yet. But if we're starting at A, we know the best distance from A to A is 0. All right, so it's basically a two-step algorithm. So initialize by visiting whatever the starting node is. So I'm going to underline this and say, hey, this is the node I'm visiting. All right, and then we do two things. First, relax distance to each adjacent node. And we'll talk about what relaxing means in a moment. And then we're going to say visit closest unvisited node. And we're just going to keep doing this. All right, so what does this mean? First of all, what is relaxing the distance? So we're trying to find distances from A. And right now, the best thing we could say is, you know, the distance from A to here might be infinity. It's not going to be worse than infinity, but, you know, it's possible there's no path from A to here. It's not going to be worse than infinity, though. So infinity is just kind of a placeholder. All right, we know that we can get to node A in a distance of 0. And if I look here, I see an edge of distance 3. Well, if I can get to A in a distance of 0 and another 3 gets me here, that means I can get to this vertex in a distance of 3. And I can do that by starting here and following this edge. And 3 is better than infinity. It's going to take less time, so I change that distance from infinity to 3. Now there's another edge connected to A, and this edge has a length of 1. So I can get to A in 0. For 1 more, I can get to this vertex. I can get here a total of distance of 1. 1 is better than infinity, so I relax that to a 1. All right, I'm done with node A, so I'm going to go ahead and circle A. And now, step 2, visit the closest unvisited node. So I circle it saying that I've visited the node. So now I want to find the node that I haven't visited yet that's closest to A. Well, what are the distances? This has a distance of 1, 3, infinity, 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 infinity. Which node is closest? It's this node down here. So I'll underline that to say I'm visiting it, and I'll go back to step 1, relax my distances. All right, I don't have to relax the distance to a visited node. Once a node is visited, I've found the shortest distance to that node. But here's an edge of length 6. Now I can get to this node with a distance of 1 from A, and another 6 is 7. I can reach this node in a distance of 7. That's better than infinity. I'll change that to a 7. I can also, from this node, which took a distance of 1 to reach, for another 4, I can get to this node. So 1 plus 4 is 5. That's better than infinity, so I'll change this to a 5. And those are all the nodes I can visit from from this node down here. So I'll circle that and say I've finished with that node. And now I have to visit the closest unvisited node. Well, I have a distance of 7, 5, and 3, infinity, infinity, infinity. So 3 is the closest node. So next I'm going to visit this node. And I relax the distances from there. 3 plus 1 is 4. 3 plus this one is also 4, and 4 is better than 5. So I'm going to relax this distance to 4. And those are the only nodes that are adjacent to this. So I'm done visiting 3. Alright, this is the whole algorithm. We just keep doing this over and over and over again. So now I have nodes of distance 4, 7, 4, infinity, and infinity. It doesn't matter which one of these 4s I pick first. So let's pick this one. And let's relax distances. So 4 plus 1 is 5. That's a better distance to here. 4 plus 2 is 6. Well, that happens to be better than 7, so I'll relax this to 6. I don't have to relax this distance because I've already visited this node. So those are the only nodes I can relax from 4. So I'll mark this as visited. And now I have nodes of distance 4, 5, 4, and infinity. So I'll visit this one. This is the closest one. 4 plus 7 is 11. That's better than infinity. So I'll relax that to an 11. And that's the only node I can visit. So I'll circle that. The only node I can reach from that node. So now I've got unvisited nodes of distance 6, 5, and 11. Let's visit the 5 next. So 5 plus 8 is 13. Well, 13 is worse than 11, so I'm not going to change that 11. So this is why we're relaxing the distance to each adjacent node. We don't just take this distance, add the length of the edge, and replace that. We only replace it if we get a smaller distance. So we know we can reach this node in a distance of 5. And from there we can go another 8 to get to B. 5 and 8 is 13. Well, that would be a worse distance than 11, so we ignore that. And that's the only edge connected to here that we might relax, so we're done visiting node 5. Alright, so the next node we can visit, looks like we've got a 6 and 11. Let's visit this. And the only node connected to it that we haven't already visited is this one. 6 plus 1 is 7. 7 is better than 11. So we'll relax that distance. That completes the visiting of this node. And now we visit B, and there's no adjacent edges that we haven't already visited. So we circle that, and we're done. Once we circle a node, we found the shortest distance. And so in this case, we've decided the shortest distance from A to B is 7. And the path is 3, 4, 6, 7. So there's the shortest path. Alright, so that's Dijkstra's algorithm. Let me do that one more time, but let me do it where we also keep track of the path. So that when we're done, we know not just that the shortest path is 7, but we also know what the collection of vertices is that gets us that shortest distance. So I'll use a simpler graph here, and I think you'll get the idea pretty quickly. So let's start off with A, and B, and C, and D, and E, and let's try to find the shortest distance from A to G. So I'll put in some distances here. Let's say this is a 1, and this is a 15, and this is a 10, and this is a 4. Throw an edge in there, and this is 1 and 2. Alright, so that might be an interesting graph. Alright, so what we're going to do, we're trying to find the shortest distance. Find the shortest path from A to G. So we start off with tentative distances, and our tentative distances are infinity, except for the node we're starting from, and we know we can get from A to A with a distance of 0. So that starts off as a 0. Alright, so we've got our 2 steps that we keep doing. First step, relax distances to adjacent nodes. Alright, so A is reachable with a distance of 0 plus 1. We can reach F with a distance of 1. That's better than infinity. So I'm going to replace this with a 1, and I'm going to write down the path. Okay, my path to A from A is just, A. Alright, so what's my path to F for a distance of 1? It's the path I take to get to A, followed by this vertex. So for a distance of 1, I can start from A and go to F. Alright, so that's one node I'm going to relax. I can also go from A to B for a distance of 0 plus 4 is 4. That's better than infinity, so I'll record a 4. And my path there is my path to A, followed by vertex B. And that's all I can relax. I've only got 2 edges connected to A. So I am done with node A, and now I'm going to visit a new node. Well, here's a node with a distance of 1 from A. Here's a node with a distance of 4. This is the next node I'm going to visit. So I'll circle that. Let's relax adjacent distances. Alright, I forgot to put a distance in here, so let me put a distance of 8 on this edge. Alright, so we're relaxing distances from F. 1 plus 8 is 9. That's better than infinity. So we can reach this in a distance of 9, and the path is the path to F, which is AF, followed by this vertex, C. So AFC. We can also go from 1 plus 10 is 11 to get to E. That's better than infinity, so we'll mark this as 11. And the path is AF, followed by E. And 1 plus 15 is 16, so we'll mark this as 16, and the path is AF, followed by G. So how do you do this in code? You need to keep track of the tentative distance to each vertex and the path. Well, the path could be a string, right? Strings aren't the easiest thing to work with in C, but we could make it work. We have an adjacency matrix, and so we can search through the matrix and find the shortest distance to each vertex, and we need a flag to say if the vertex has been visited or not. So this is codable. It's mostly a housekeeping challenge. All right, so F, we relax the distance to the 3 unvisited nodes. We're done with F. Let's circle that. Now we need to find the closest vertex to A. Well, we have infinity, 9, 11, and 16. So it looks like 9 is going to be the closest. So we're going to visit C. And what can we relax from? Oh, sorry, we have a node of distance 4. So let's visit B next. So what can we relax from 4? 4 plus 1 is 5. So we can get to D for a distance of 5, and the path is AB, followed by D. 4 plus 2 is 6. We can get to node C for a distance of 6. So let's relax this. 6, and the path is AB, followed by C. And that's all we can visit from B. So we'll circle that. So unvisited nodes, we have 5, a 6, an 11, and a 16. So the next thing we're going to visit is D. And what can we relax from D? Well, 5 plus 1 is 6. And that's not any better than what we already found. So we could replace it, or we could just leave it as it is. We'll leave it as it is. 5 plus 8 is 13. That's not better than 11, so no advantage there. So we're not going to end up relaxing anything, and we're done with D. All right, now we have a 6, 11, and 16. Let's visit this node next. So what can we relax from 6 that we haven't already visited? Well, 6 plus 2 is 8. That's better than 11. So we'll replace this distance with 8. And the path is the path to the node that we're currently visiting, ABC, plus this vertex, E. And that's it for nodes we can visit from 6. So we'll circle this from C. And now we have 8 and 16, so let's visit this node next. And 8 plus, well, the only node we haven't visited is here. 8 plus 1 is 9. That's better than 16. So we'll mark this as 9, and the path is A, B, C, E, right? The path to this vertex E, followed by G. And that's the only thing we can get to from E. And now the only unvisited node is G with a distance of 9. And there's nothing we can relax because all the other nodes are visited, so we can circle that. And so we found the shortest path is 9. And the path itself is from A to B. So right along here from B to C. And then from C to E. And then from E to G. So 4, 6, 8, 9, shortest path. And again, it's not the shortest number of steps. We could go 1, 2 steps, but that 15 is going to make this total path longer. It's going to be 16. So this always finds the shortest path. And this is an example of a greedy algorithm, right? As we proceed, we are solving the problem at each step, right? Each time we circle a node, we have found the shortest path to that node. And we never need to reconsider the distance to that node. Each time we visit a node and circle it, we're done with that node. So we're building up the solution as we proceed, and when we're done, we've got the solution to the whole problem. All right, so that's a really brief overview of graph theory and Dijkstra's algorithm, and you get some practice problems to work on that algorithm and think about processing this data in a program, so reading in adjacency matrices and answering questions about them and so on and so forth. And then we'll probably have a programming assignment where you get to code Dijkstra's algorithm and solve this shortest path problem. All right, that's all we got for now. Thanks.